Okay, as I said, that's pretty neat. But it's neater if you look at this geometrically in terms of the eigenvector basis, because then you understand that picture I drew a while ago, just based on what happens from a few transitions, extrapolating and so forth, and you see exactly what happens. You get a geometric approach, geometric sequence with common ratio 0.7, one eigenvector, right? Approaching the limiting population. So to see why that happens, you do the eigenvector basis. And I'll do that in green. So I'm just going to use 2, 1 for one of my eigenvectors. Actually, I could use 2/3 of 1,000 and 1/3 of 1,000, because that would model our, but I'm just going to do it in terms of these eigenvectors, okay? And then we have negative 1, 1. Okay? So we'll call this P1 because that agrees with notation in your book. And we'll call this P2. Okay? And now we've got our population vector, which is 500, 500, but that's way off the scale here. So we're just going to have an arbitrary population vector, okay? But with the same conditions. And maybe this is in hundreds or something, okay? Maybe these numbers are in hundreds, we don't care. Okay, well, let's call this our population vector. I don't want to use P for the population vector. Okay, so I'm just going to call this V naught, the vector we start with. Okay? Well, V naught can be expressed in terms of your eigenvector basis. I'm just thinking notation here, but here's, you go out along this eigenvector, it's something I showed you very early in the course, right? And you also project this on this eigenvector. Okay? So that V naught is equal to this vector that I still don't have a notation for, but I'll come up with some. And this one. Okay? So actually I've got a notation, very simple. This is on I'm thinking ahead and not having a good time with it. Okay, this is C1, P1. And this, squeezing in on my labeling here, I should have drawn the vector somewhere else, but C2, P2. Okay? Now what's a transition do? Take C1, P1 to C1, P1. Why? Because P1 is an eigenvector with an eigenvalue of 1, right? P1 is an eigenvector, its eigenvalue is 1. Because as we found out, back on the previous board, the vector with eigenvalue 1 was the 2, 1 vector, right? Okay?
C1, P1 to C1, P1?
Yeah.
Okay.
Because we do the transition on C1, P1, well, the transition is C1 times the transition of P1, right? What's the transition do to P1? It maps it onto itself because it's an eigenvalue, it's an eigenvector with eigenvalue 1. Okay? And P2 is an eigenvector with eigenvalue 0.7, right? Well, geometrically, that means this one doesn't change. This one gets shortened by 70% to 70%. Gets 30% shorter, right? So that the transition of V1, I haven't used the T notation, or transition of V0 equals the transition of C1 P1 plus C2 P2, and I'll write it all out, which is C1 times the transition of P1 by linearity, right? Constant multiple. Which is C1 P1 plus C2 times 0.7 P2 Now I set it up here, and I wrote it out formally here, just to be sure that I'm not invoking superstition up here somehow. Okay? You know, do what intuitively I'm sure is correct, and don't trust myself, but write it out rigorously to be sure. We need to do this. Okay? Make sense? So, what's this tell us? It tells us that after transition, we're still going to have C1 P1. We're all going to have 7/10 of C2 P2. So here is our vector, which agrees with our picture over here in the picture I showed you last time, which is pretty much the same as the picture I got there. It's pretty much the same as this, except I got prettier colors there. Okay? Well, what's going to happen next? Well, this thing is now C1 P1 plus C2 P2. When we do the transition, we're still going to get C1 P1, because transition doesn't change P1. But P2 is now going to become 7/10 of what it was. And so this is going to shorten to 70%, then 70%, then 70%. That's a geometric sequence. Okay? So what we get is for any vector, okay, we start, I'll go ahead and use the same colors, okay, except for the sequence. So we've got our V0, and we've got
about that.
I can draw this at any length. I'll just draw it long this time. And see, I drew that green. That vector is supposed to be green. Okay? Then I used the orange for the components. So I project down here. Okay? And you know, when I say I project, that was a little careless. I kind of projected this at a right angle. I've got to project parallel to this one to get a component in the direction of P2, right? So I'm going to be a little more careful. So, you know, P2 is actually more in this direction, right? It's not a perpendicular projection. We're not doing orthogonal projection. We're doing projections Well, they are